Today we are going to do a simple finite element heat transfer tutorial, and I'll be using the open source programs Elmer and Gmsh. And I'm using this very simple geometry to start with. We have a wall with a glass window, uh, and the window is 2 millimeters wide and 25 millimeters tall, and this is just a cross section, so could be the depth of this figure, could be anything. And to start with, we'll start with this very simple condition where on the outside is very cold, -5 degrees Celsius, and on the inside is a warm 22 degrees Celsius. I'm starting with this simple problem because the goal of this tutorial is to learn how to run a steady state heat conduction problem and a transient heat conduction problem using these software platforms that are openly available. And I didn't want to complicate the problem by introducing complex boundary conditions and geometries. A very good book for learning the details of these types of problems and how to solve them in many different ways from the fundamentals is this book, Heat and Mass Transfer. Now let me move on to a little bit of the fundamentals that you can find in textbooks. So the heat equation can be written as the rate of change of temperature with respect to time is equals to alpha times the spatial second derivative of the temperature, where alpha is related to the thermal conductivity, density, and specific heat capacity of the material under consideration. So let's say this material is made of glass and it has its thermal conductivity, density, and specific heat capacity as a constant, so it is a homogeneous material. And the boundary conditions on this side of the wall or this side of the glass is a warm 22 degrees Celsius, and on the other side, similarly, it's a constant temperature boundary condition of -5 degrees Celsius. So in the steady state, uh, what you will see is that the rate of temperature with respect to time is 0, and if you substitute that here, it doesn't really depend on the material constants. Later, when we look at different thermal conductivities, different materials in the same problems, or when there is a change with respect to time, then obviously these things will come into play. But if we consider the steady state where the temperature has already stabilized, you can imagine that the temperature is high here and low here. So there will be a gradient of temperature within this thickness of glass. So to do a two-dimensional simulation, we need this boundary, and what to do about this and top and bottom boundaries of this rectangle. So to simplify, we will just assume that these are insulators, which means that there's no heat flux. And if you go back to the fundamentals, which I won't cover here, that will mean that the second derivative of temperatures are 0 at these boundaries also. I'm now going to demo using Gmsh to creating the rectangular geometry and mesh. And I found this tutorial to be a good guide to do that. So let me start by opening a terminal, and as you can see, I already have a Gmsh sandbox that I tried before. So let me make another one to try out this problem. And I'll use the Gmsh to create I'll call this file the rectangular window. So to create a rectangle in Gmsh, what you do is you first create 2 points, join them with a line, and then extrude it. Add point at 0, and then I'll create it at 0 and 2 millimeters away. So now I have, so I did it in Y instead of X. So let me try to remove that. So the easier way to do it is probably in the text file. So if you look at it, there's already that, and I can edit it. So I don't want this, and open it again. So it's already there. And then I'll add a line between those 2 points. So once you get the line, you'll see that it'll say, it'll ask you to press Q to finish. So once I've done the line, I'll press Q. And then to create the surface, I'll extrude this line. And in the Z direction, or Y direction actually, I'll extrude it 25 millimeters. Let's see if I do end selection. If I'm in this window and do end selection, so I now have a rectangle that's 2 millimeters wide and 25 millimeters high. So from this rectangle, I have to create a surface that you can assign a boundary, or where you can mesh it. And also, to define the boundaries, I have to make these lines physical and not just geometric entities. So say add surface. So I select this surface and make this surface physical. And then the lines, I want them as boundaries. So I select one by one and then press E to end selection to create a separate boundary. Otherwise, they'll all be the same boundary. E, E, E. So now I've created the geometry. Let me look at what it looks like in the text file. So I can close this and edit the text files. You can see there are 2 points and a line between those 2 points, and it's extruded by 25 units to create that rectangle. And that rectangle is defined as a physical surface. The physical lines are then defined to create the physical boundaries. So now if I go back to Gmsh, I can create a mesh. For example, if I do the 2D mesh, I created a mesh. This mesh looks particularly coarse to me. There are not too many elements, which might or might not be fine depending on the problem. I usually like a finer mesh, so I'll try to create a finer definition for the mesh. So element size at, so you remember this is 2 millimeters, and if I go back to this, you can see the element size is 1 millimeters at these points. So maybe if I just edit this, it might work. So if I make this half of 1, it might create a finer mesh. So I'll keep this open so that I can update the mesh over there, and I'll open Gmsh from there. So the sandbox, Gmsh, and rectangle geometry. If I mesh it now, you can see I created a finer mesh. So if I want to create an even finer mesh, for example 0.25, 0.25, and then save this file and mesh again. So it didn't update because this is not loaded, so I load it again, and you can see it created a finer mesh. So the fineness of this mesh, I like it now, so I'll just save the mesh and close this. So if I look at this, there's the mesh. Now if I, this mesh is in the Gmsh format, and Elmer requires it in the Elmer grid format. So to convert it to Elmer grid, let me run Elmer grid. So you can see Elmer grid is already there. And if I look at the documentation for Elmer grid, the Gmsh format is number 14, and the output format I need in the Elmer solver format, which is number 2. So what I need to do is Elmer grid 14 to 2, and the name of the file is rectwin.mesh. So it seems to suggest that it created the mesh. So in the folder rectwin, if I go back to rectwin and look at the boundary, for example, there's no, so if I edit the boundary, you can see that the boundaries are named 9, 7, 10, and 8. So now I'll open Elmer GUI to continue the rest of the project. So in Elmer GUI, first I have to import the mesh, say load mesh, and I select the right folder where the mesh is kept, and you can see the mesh has been loaded. So just to be on the safe side, I'll save the project. This saves into the folder, and then I have to do some model setup. So by experimentation, what I found is that I need a little bit more of the steady state max iterations than one. So it has to be 2 or more for the output to be in the correct iteration. So otherwise you'll just get the starting point as the output. I'll explain that a little bit more. That might be a bug or a feature. And then we also need minimum iterations. Steady state min iterations equals to 5. I'll put at least 5 iterations, output intervals. So these intervals are how many outputs it will generate. So in the steady state, there's no concept of time, but still it considers each calculation for conversions as a time step. So if I do this, then 0.1 seconds between time steps. It doesn't really matter for steady state. The big thing for steady state is the max iterations. So I apply this. So I've set up the system. The output is by default VTU in this Linux system. In my Windows system, this was the Elmer post. So for some reason, the Elmer post didn't work, and we stick to VTU over here. Apply, and then we set up the equations. We always need results output, and each equation is related to a body, so the body is the whole domain over here. And the output format for this, I'll set it to VTK instead of VTU. It doesn't really matter. And I'll put in a heat equation. So the equation is heat equation. Material. So for the, as I said before, for the steady state, the material properties don't matter too much. But what I found is that if you don't put the material properties, then the system might crash or might generate an exception. So you add in material, and you don't need initial conditions or body force. You could have them, but the initial conditions are the starting temperature, but in the steady state everything calculates out to be depending on out to what we set for the boundary conditions. So let me add the boundary conditions. Be sure to check the right tab. So starting temperature -5, I'll name that M5, or the constant temperature boundary condition. I'll add one more boundary condition called 22 Celsius, and I'll call it P22 for positive 22. And then I'll add another boundary condition called zero, zero flux, or ZF. And then let me make this bigger so that it's easier to see. Let me set the boundary properties using this user interface. Double click on the boundary, and that one's -5. Double click on this boundary, that one's positive 22. Double click on this boundary. No, that's not a boundary, so cancel that. Double click. No, I don't need that one. So let me just select the right boundary condition. So this part of the open source tools is a little bit buggy, if you will. So let me select this one as use as body and see if that works better. So it's still difficult for me to select this. Let me see if it's better if I um, zoom in. So I'm trying to figure out how to move this. Let me just try to select this. Boundary 6. I don't think that's the right boundary, so let me just go to um, let me go back to the model boundary condition ZF, and the remaining boundaries 7 and 9. I'll say update OK. So that's a little bit tricky with this open source tools, is to find out whether the boundaries are correct, because it's difficult to select. So if I do, it can be tricky in other tools too, but it's more tricky in the open source ones. So if I do the boundary index, you can see that one's 7, that one's 9, and that one's 8, and that should be 10. If I zoom in really well, I can see that that's 10, so that's now correct. And boundary conditions are all set, so I save project and I generate the file for the solver information file and look at it a little bit. So if I look at this is something that I added to the options that were not already there. Steady state min iterations, and this is similar to steady state max iterations, except I set the min to 5. And then I look at everything else, looks fine to me. The boundary conditions 22 -5 and 0 flux. So now I can finally go ahead and start the solver. So as you can see, it took 5 iterations and decided that it converged. If I had set it to if I hadn't set it, then maybe it would do just one iteration, and sometimes that seems to be problematic. For example, if I try to use the Elmer post, the Elmer post doesn't exist. A file doesn't exist for this. So let me see if Elmer VTK works. And as I remember, even this one uses the Elmer post format. So the only option I have is Paraview, which is much better. So I think the developers decided that because the functionality is available in Paraview, they won't implement it again. So rectwin. So we created several outputs, both VTK and VTU. Let me open the VTK one. I think it's similar. It will display similar. So you can see, I'll remove the color map for now. There is the cross section of this window, and there's 22 degrees, minus 5 degrees. What about this? I think it's supposed to be a little bit more uniform, and that's what I mean by you need more iterations. So the first output of the iteration is the initial condition, and after the first iteration it converges to a correct value. So that's just because of, and that is shown as a time step in this para view, but it's actually just iterations of the steady state case. Now to look at it x versus temperature, what you can do in para view is once you apply this uh, toolbar becomes available, and there's a thing called plot over line. So that's a pretty good line, but what I want is probably more like this. And I'll just set zero point 0.1 to be 0 and 12.5 and zero point 0.2 to be 2 and 12.5. So it's just a cross section near the middle of this window, and apply it. You can see that the temperature varies from 22 degrees Celsius to minus 5 degrees Celsius in a linear manner, as we expect. And if we go to the 0th iteration, you can see it's 22 and 5 and 0. That's the initial value that was set in the numerical method. And this part is just interpolation due to the coarsity or the fineness of the mesh. So if you look at this and display the mesh, let me see if I can figure out how to do that. It might be uh, one of this view sources, filter, tools, edit. Yeah, I can't see how to display the um, not tooltip. Yeah, so I have to go back to close the plot line and go back to case zeros to display this with edges. And you can see there's some interpolation within the elements, but the elements themselves are set to 0. And now if I go back to plot over line, you'll if I display that again, okay, render view, line chart view, yes. So that one's fine. And in the line chart, if I do that, then you can see that now in the second iteration, this is much more proper. The actual data are just from the points. Everything else is interpolated within the elements. So thank you for watching this part of the tutorial. In the next part, I'll try to create something with a transient um, simulation and also with multiple materials.